Hi, I am Alex Lima, and I will present our work entitled Real-Time Simulation of Accommodation and Low-Order Aberrations of the Human Eye using Light Gathering Trees. This is a joint work with Arthur Medeiros, Vitor Marques, and Manuel Oliveira from the Federal University of Rio Grande do Sul in Brazil. How do people see the environment? Well, this might sound like a silly question with an obvious answer, but not everyone sees their surroundings the same way. Perhaps due to eye aberrations or some other condition, everyone has a different first-person experience of the world. What if we could step into someone's shoes and perceive everything around us exactly like they do? Like if their eyes were ours instead. This is what we want to achieve. A very challenging aspect of realistic vision simulation is dealing with partial occlusion effects. Here we have an example of such issue, a picture of a plant in the foreground and the wall in the background. In this case, the plant leaves act as occluders. The foreground is in focus and completely blocks the background image in certain areas, acting as a binary mask. However, when the background is in focus, we have see-through effect throughout all the foreground, and the background wall becomes almost completely visible. Here we have a sideways diagram of the plant and wall picture. When focusing on the plant, rays emerging from a finite area of the background converge to a single point on the retina, or image plane, causing the wall to appear blurry. At the same time, rays emerging from a single point on the plant converge to a single point on the retina, causing the foreground to look sharp. However, when focusing on the background, we have a different situation. A single point on the background together with a bunch of rays from a finite area on the occluding plane will be mixed into a single point on the image plane, causing the see-through effect. What is worse, points that were previously completely occluded when focusing the foreground now also contribute to the formation of see-through parts of the image. This is a problem when we want to use pinhole-like images as input for aberration simulations, because the color and depth information of those background points will be missing. If, however, we somehow have that information, we can use geometrical optics to construct a simulation of that scene as viewed by humans with arbitrary accommodation or eye aberrations. Our contributions include a technique for achieving a real-time simulation of human vision considering real scenes with arbitrary depths and taking into account low-order aberrations like myopia, hyperopia, and astigmatism, and also accommodation, and a tree data structure that can be used to accelerate vision realistic rendering, which can also handle partial occlusions among the objects in the scene, when in the presence of a finite pupil. Some previous works related to ours include a method that introduces object space point spread functions, where a scene is discretized into planes and histograms at each plane are used to construct PSFs, depth of field rendering using pyramidal image processing, real-time lens blur effect and focus control, and layered depth of field method for solving partial occlusion. Our work distinguishes from these techniques in the sense that it works in real time with real scenes with depth information, not only synthetic ones, and we also have made objective measurements to attest the validity of our simulations when compared to ground truth. Before moving to the description of our technique, I'll present an overview of low-order aberrations from the perspective of geometrical optics. In normal non-accommodated vision, incoming parallel rays of light converge to a single point on the retina, forming a perfect clear vision. In myopia, those same parallel rays converge to a point before the retina, causing positive defocus. In hyperopia, those rays would converge to a point after the retina, causing a negative defocus. And in astigmatism, instead of a single point, rays converge to line segments at different distances from the retina, so that an astigmatic patient doesn't have a focal point anywhere, and images will always appear distorted towards some direction. In order to perform our simulations, we use as input real scenes represented by pinhole-like images with color and depth channels. All the images shown in our examples were obtained from this online dataset. The idea behind light gathering trees is to achieve the outcome of ray tracing without casting several rays during runtime, by using a data structure, a weighted tree. In order to do that, we discretize our scene into several planes, regularly spaced in diopters, and in an offline step, we perform the ray casting from the lens plane to an arbitrary virtual scene, recording ray plane intersection information in that tree to be used during runtime. As expected from a traditional ray casting approach, several rays contribute to form a single pixel output, and we use the same tree to simulate the outcome of every pixel. These data structures don't need to be different across the visual field because we assume the point spread function, or PSF, is the same on every direction. This is the so-called isoplanetic assumption, and it is used because the outcome of our simulations is not a representation of the state of the retina at a given instant of time, but a picture that will be seen by someone. A sequence of tiny images captured by the fovea is used to build a full mental picture of the scene by means of a quick eye movements called saccadic movements, and so we require that every point in the image should be viewed as it was imaged by the fovea. Several other works make the same assumption, sometimes implicitly and other times explicitly. This image shows how the rays propagate through the pixels that exist on the planes. We call these pixels in object space cells. An important performance improvement comes from noticing that several rays may intercept the same cell, and as such, they can be grouped into bundles or beams and treated as a unit. These beams are associated to links between tree nodes. If we group rays into beams, it becomes evident that the structure is actually a tree. In this picture, we use arrows with numbers to represent the groups of rays and also weighted tree nodes. Ray tracing in this case is equivalent to traversing it from the root to every leaf, or until some obstacle is hit. This tree can be pre-computed. It will only be recomputed if visual parameters like focus of interest or aberration are changed. We will now see what happens in some important cases encountered when casting rays. What happens if there is an occluder on the closest planes? The occluder causes color information on the subsequent planes to be missing. The rays that should be hitting the occluded region will land on regions without color information, most likely causing artifacts. The heuristic we use to fill the missing information is to use the color data from the previous traversed cell, that is on the previous plane. The color information beneath this cell is usually very similar to the occluded one, and it is our best guess. We can extend that information to the occluded region and prevent artifacts. This can be done during runtime. We will now start showing results of our technique in real scenes. The first one shows a blue and white flower at 0.5 meters from the viewer, a red flower at 1 meter, and a game box at 2 meters. This is the depth information of our first picture. And here we show the plane discretization of our scene, where each color corresponds to a single plane. This is a simulation of myopia with 2 diopters. Note how the blue and white flower in the foreground appears sharp, while the background game box looks blurry. A simulation of accommodation at 2 meters, where the game box is, results in loss of focus on the flower. And now the game box is properly focused. Here we see the same cases compared side by side with the original pinhole-like image. This is the case of myopia, and this is for hyperopia, or equivalently accommodation at 2 meters. We compared our technique with GPU path tracing for simulating the view of myopic subject with 3 diopters on an NVIDIA RTX 2080 Ti GPU. Our technique is capable of tracing 314 rays, constructing the tree, and using it to perform the simulation all under 6 milliseconds, producing this image. Using the same time budget, GPU-accelerated path tracing can only trace 2 samples per pixel, causing the result image to look grainy due to the path tracing's stochastic nature. Here we have our second example, using a picture of a backpack in the foreground and a broom in the background from the same online database. This is the depth channel of our image. This is a simulation of focus at the backpack. Note how the broom gets blurry in the inset when compared to the original reference image, also in the inset. This is a simulation of focus at the broom. In the inset, we can see that the backpack is now out of focus. Here we'll quickly go back to the previous slide to make a better comparison of a focused backpack with a defocused backpack. Here we have our third example, using a picture of a moose puppet in the foreground. The front and back parts of the bucket rim are at different depths, so they should be rendered differently depending on the focus. This is the depth channel of our image. This is a simulation of focus at the moose puppet. Note how the shirt and the back rim get blurry in the inset. This is a simulation of a subject with myopia and astigmatism. Note how different directions present different blurriness levels. We validated our results using single-plane images, given the difficulty in acquiring RGBD images of complex scenes with perfect depth information, which is essential for the technique to work properly. We obtained very strong agreements between ground truth and simulation images, with SSIM and PSNR bigger than 0.93 and 32.3 respectively in all comparisons. In summary, I presented a real-time technique that can be used to simulate accommodation and low-order aberrations of the human eye, considering real scenes as opposed to synthetic ones. I also presented a novel data structure, a light gathering tree, to accelerate such simulations. And here I list interesting ways to extend our work. First, the combination of our technique with tracking technologies in virtual reality. This is a promising application since our trees wouldn't need to be recomputed for the viewer translation and orientation changes. Implementation of trees that can handle diffraction effects for microscopic environments, for example, where these effects are more significant. And finally, include higher-order aberrations in our simulations. They are not so prevalent as lower-order ones, but they definitely exist and should be considered. We would like to thank our sponsors, the dataset provider for the RGBD images used in our work, and everyone else that helped us with this work. Thank you all for your attention.